Hello everybody. We move on in this video to functional limits. So we've spent quite a bit of time looking at limits of sequences, which I'll remind you at the start here, right? When we have some sequence A dot, this is a function whose domain is the positive integers. And the codomain for us, right, has been either the real numbers or some other subset of the real numbers. So we could write it like this. Okay. We would like to generalize the notion of a limit of a sequence to functions that don't have to have the positive integers as their domain. So actually, that's how we'll just start this off. So let's let f be a function from some domain D to the real numbers. Okay, and when we want to talk about the limit of a function at a point, we're going to somehow rely on this sequence stuff anyway. What we're going to want is that the point we talk about is somehow a limit point of the set D. So I'm only going to be looking at points where I can approximate A with elements of D. Okay, that is, I can build D sequences that converge to A. Okay, so with this setup, we say that the A limit of f equals some real number L if, well, what should this mean? Well, let's draw a picture. All right, so now I have D, and D, I'm drawing it like it's this nice continuous subset of the real numbers, but it may be the rational numbers or something funny, right? So you might have some gaps in here, right? That could be. Okay, in fact, the gaps could be, very frequent. We don't know. Okay, and then I have the real numbers over here, and then there's A somewhere. And you'll notice I haven't drawn A sort of, as an isolated point kind of away from everything, because we're assuming A is a limit point of D. All right, now actually A doesn't have to be in D itself, right? I just has to be a limit point. So let me put a little hole possibly around it, because I'm not claiming A is in D, only that it's a limit point. So I can certainly approximate it with things in D. All right, and then over here I have some value L. Okay, now I'm not going to say that f of A is equal to L, because f of A may not even exist, because A may not be in the domain of the function. All I'm saying, right, all I want to say is that as I get close to this point A, the outputs of f should get close to this point L. All right, now how do we make that precise? Well, to get close to L, that means we're going to want to put some sort of L coin down, right? So I have some L plus epsilon, some L minus epsilon. Yep. So my claim is that I can get near L as long as I get near A. So I'm going to have to put some sort of coin down around A. All right, so I put some coin down, and it might be that the coin you write down isn't completely inside of D, right? So you might write down a coin and only part of it is inside D. That's fine, right? So, but we want that whenever we do this, all the points inside that coin that are also inside D are mapped by F into this L coin. All right, so the precise definition then is if every L coin is going to contain the F image of this A coin, well, not entirely, because you only get to choose points that are in D. So it's going to contain the F image of the intersection. Okay, so I need to intersect this coin with D. So the intersection of D and a punctured, oh, I didn't mention this before, but right, we don't know that A is even in D, right? That is, A may not be in the domain of F. So we don't actually want to have to evaluate F on A. So we take the punctured, or a punctured A coin. Okay? So now we're not saying for every punctured A coin intersect with D. We're just saying if you have an L coin, it will contain the F image of the intersection of D with some punctured A coin. Okay, and in this case, the notation, this is what you probably remember from Calc 1, is that the A limit of F equals L, right? So the limit as x approaches A of f of x equals L. Okay, and so the key idea here, right, is we can get close to L by getting x close to A, but we are not making x equal to A. Now, there's a more standard definition, right, that you'll see, for example, in the textbook, right, which we're going to translate this all into epsilons and deltas. Okay, so this is the symbolic form. So first, we need to choose, right, some L coin. All right, fine. So for all epsilon greater than 0, right, epsilon is the L coin radius. Okay, then there needs to exist some A coin, right? So here I could have maybe called this A plus delta, A minus delta. Okay, so there exists some delta, which of course depends on this epsilon. Okay, and so this is your A coin radius, right? It'll even be a punctured A coin radius, but that doesn't matter. Okay, such that, well, we want the L coin to contain the F image of the intersection of D and this punctured A coin. Okay, so such that, well, we could write this in a couple of different ways. So here's first the standard one. If x and A are less than delta of epsilon apart. So that means my x is inside this A coin. But I also don't want x to equal A. So the way I handle that is by assuming that the distance between x and A is not equal to 0. That says, right, so this part here tells us x is in the A coin of radius delta of epsilon. And this bit here is telling us x does not equal A, right? So this gives us the punctured part. Okay, so if you're in here, then you apply F. So then, if I apply F to that point x, then it should be in this L coin of radius epsilon, which tells me that the distance between f of x and L is less than epsilon. Okay, so that's the symbolic form. Okay, alternatively, right, so alternatively, okay, well, the for all epsilon, there exists delta, that's the same. But what we would be saying is if I apply F to the punctured A coin of radius delta, okay, so there was our notation for the punctured A coin, that this is contained in the punctured L, or not the punctured, but the L coin of a radius epsilon. Okay, so that's a short way of writing these two statements with absolute values. All right. In practice, we're often going to want to use, though, this longer form version. All right, but this is, I mean, you can really read this off from the words we used, right? For all epsilon, okay, that's giving you an L coin. There exists a delta that gives you an A coin, okay, such that the F image, there we go, of this punctured A coin is contained in the L coin. All right, and oh, of course, we're forgetting something here, right? We need to intersect with D. All right, in fact, we forgot that over here too, right? So such that if this is true and x is an element of D. Okay, so this is something that's very easy to forget as you're writing things down, but as you make your domain more and more exotic, then this is something you have to keep track of. Okay, now of course it could be that the limit doesn't exist, right? That is, there is no such L for which the a limit of f is equal to L. So in that case, right, so if no such L exists, well, then we say that the limit as x approaches a of f of x does not exist. Okay, so it just does not exist. Of course, there's some special cases, right, where it does not exist because we know the limit is infinite, right, or negative infinity, something like that. Okay, that'll get handled in the homework. All right, so let's do maybe an example or two so we can see how we actually use this definition to prove things. So let's say I was looking at the limit as x approaches 2 of 5x minus 3. Okay, so you think about that for a second, and remarkably, everybody comes up with the answer 7. And how is everybody coming up with that answer 7? Well, probably what you're doing is putting the 2 in for x. Okay, which is exactly the thing, right? We said you're not supposed to do, right? We're supposed to put a little hole at this a, right? We're not allowed to do that. Now, secretly, right, in the back of our minds, we're going, yeah, but 5x minus 3 is a continuous function, so you're really allowed to just evaluate the limit at 2. Okay, so that's true. But let's just say somehow, some way, you guessed that this answer was 7. Okay, now we want to try to prove that this limit really does exist and equals 7. All right, so let me, just for simplicity, give a name to my function. I'll call it f of x. And so I want to show that for every 7 coin, okay, so 7 is supposed to be the limit, that the difference between f of x and 7 can be as small as I want. All right, so maybe we'll start with some epsilon greater than 0. And I want to look at the difference between f of x and 7, and I want to somehow get this to be less than epsilon. Okay, so this is the goal. The goal is to get this difference to be less than epsilon. Okay, well, let's see what this difference actually is. So f of x is 5x minus 3. And when I subtract 7 from that, I end up with 5x minus 10, which I immediately notice I can factor a 5 out of, and I get 5 times the quantity x minus 2. Okay, so I can take this absolute value and break it apart. The 5 is, of course, when you have absolute value 5 is just 5. And then I'm left with the absolute value of x minus 2, or the distance between x and 2. Okay, so my goal was to get the difference between f of x and 7 to be less than epsilon. And I have rewritten that difference as 5 times the difference of x and 2. So if I want to get this to be less than epsilon, what I could do is, well, what if I made this less than epsilon over 5? All right, if I made this less than epsilon over 5, then 5 by epsilon over 5 would be less than epsilon. Well, am I allowed to do that? Well, remember my goal. Okay, let's go back to the picture that we had. Okay, so I have 7 here, and I put this 7 coin of radius epsilon around it. So there we go. I want to get inside there. And what happens on the other side? Well, I pull out a little dot where the 2 goes. Why 2? Because, well, I'm taking the 2 limit. All right. So I'm supposed to put some coin around 2. There we go. A 2 plus delta, a 2 minus delta. And things in this coin are within delta of 2. And I just need to figure out what the right delta is. But that means I'm asking what is their distance from 2, and that's exactly what this absolute value of x minus 2 does, right? This precisely tells me distance of x from 2. And so in fact, what I'm saying is, oh, just make that distance less than epsilon over 5. So why don't I make my delta epsilon over 5? And then we would be good to go. All right, so thus, if x and 2 are within epsilon over 5 of each other and greater than 0, right? I don't really care about what happens when x equals 2, even though I actually know it's going to work, wink, wink. Then the distance between f of x and 7 is going to be less than epsilon. Okay, so this implies that the limit as x approaches 2 of f of x is equal to 7. Okay, so that's all there is to it. Now in the homework, of course, I have you prove something called the inspired choice theorem, which we already had for sequences, but it also works for functions. And that would have told us, instead of being clever and making this inspired choice of epsilon over 5, we could have just put epsilon down here. And if we'd have done that, right, if we'd have said if x minus 2, an absolute value is less than epsilon, then the distance between f of x and 7 would be less than 5 epsilon. And you say, well, that's not less than epsilon. Yeah, but the inspired choice theorem says it doesn't matter. As long as you have some positive constant times epsilon, that's good enough. Okay. All right, let's do another example. This is a classic example. Every Calc 1 class, I don't know, the history of, I don't know, last 200 years has probably done this example. So we're going to have a function g of x given by x squared minus 4 over x minus 2. And we want to show that the limit as x approaches 2 of g of x is equal to 4. All right, so how are we going to do this? Well, again, let's start with choosing some 4 coin. So that means we need an epsilon. All right. Now, I want to know what's happening between g of x and 4. What's this difference? Of course, I know what g of x is. It's x squared minus 4 over x minus 2. All right. Now, here's the beauty. We are only going to be looking at coins on the left. Okay, so here I have a 4, and I get some coin, right? 4 plus epsilon, 4 minus epsilon. But when I come over here to 2, and I look at its coin, I'm looking at punctured coins, right? I'm assuming that x is not equal to 2. So why is that going to matter? Well, let's put down here, x squared minus 4, actually we'll do it up here, this is the same as x minus 2 times x plus 2. Okay, that's that numerator. And so I can cancel the x minus 2's provided that x does not equal 2. And because I'm only looking at punctured 2 coins, I'm assuming x does not equal 2. So since x does not equal 2, I can cancel the x minus 2's, and I just get x plus 2 minus 4. Of course, this is the same thing as x minus 2. And this is amazing. I'm trying to get that g of x and 4 are within epsilon of each other. And I've shown that that distance is actually just the same as the distance of x and 2. Well, geez, that's just asking me for how big I want this 2 coin to be. And if I want this to be less than epsilon, well, look, I just make this less than epsilon. Right? So let's summarize this. If x and 2 are within epsilon, then g of x and 4 are within epsilon, provided that, of course, x and 2 are not equal to each other. Okay, so thus the limit as x approaches 2 of g of x is equal to 4. Okay, let's do one more example in this video, except this will be a non-example. So our third function here will be h of x. And h of x is going to be a piecewise defined function. So it's going to be 3 until you get to 7. Then when you get to 7, right, and well, just after 7, it's going to drop down to 1. So pictorially, you have 3, you have 1, there's going to be 7. So the function passes through 3, gets to 7, then it's going to drop down to 1. All right. So that's what our h of x looks like. Okay, so my buddy Clever Carl comes around, and what does Clever Carl thinks? What does he think? Clever Carl says h of 7 is equal to 3. Right? We actually know that at 7 the value is 3, and as x approaches 7, well, you see as you approach 7, h of x equals 3. Thus, the limit as x approaches 7 of h of x is equal to 3. So that's what Clever Carl says. Okay, but of course Clever Carl's never right. So let's see what's going on. Okay, so he claims that. We're going to try to prove it. All right, so maybe we said, okay, fine, let epsilon be greater than 0. And I want to make an epsilon coin. Okay, fine. In this picture, we're going to be putting a coin around 3. So there you go, right? There's 3 plus epsilon, 3 minus epsilon. Okay, so that's our coin around there. And now let's look at the difference between h of x and 3. And the thing is because h is a piecewise function, the difference between h of x and 3 depends on which x we choose. So if x is to the left of 7, or even equal to 7, then the value of h of x is 3. And so I'd get 3 minus 3 in absolute value, or just 0. Hey, 0 is less than epsilon. Not too bad. But what if x is greater than 7? Well, if x is greater than 7, then h of x is going to be 1. And so I'd get the absolute value of 1 minus 3, which is 2. So what this is telling me is if I make epsilon less than 2, okay, so let's say epsilon equals 1, then I know that this is definitely above the 1, right? If I made epsilon 1, then 3 minus 1 would be 2. And now all these points that are to the right side of 7, okay? So I'm putting a 7 coin down. All these points to the right are not inside, right? Their image is not inside the 3 coin. Okay? So if we drew this using our vertical lines, so there I have my 3, and let's put down here 3 plus 1, which is 4, and down here 3 minus 1, which is 2. So I have a 3 coin of radius 1. And then over on the other side, I have my 7. All right. And, well, I actually know that at 7, the value is 3. That's true story. Now, if I put down any coin, all the stuff up above 7, right? So not including 7, but all of this stuff, where does it go? All this stuff goes to 1, right? And 1 is down here. So all this stuff goes to 1, which is not inside the 3 coin. So this shows me that the limit cannot be as x approaches 7 cannot be 3. Okay. On the other hand, right, we know all this stuff down below, that is going to map over to 3, right? That actually does go into this 3 coin. And this would be outside of a coin around 1. So this also tells us that 1 is not a limit. Okay? In fact, nothing is going to be a limit. Okay? So the limit as x approaches 7 of h of x does not exist. Okay? Okay, well, I think that's enough for this video. So next time, we're going to go over some properties of functional limits. See you next time, everybody.